Thank you very much. Thank you very much to the organizers for the invitation to speak here. I was very glad when I received the invitation. And yes, my family name recently changed from Hutzler to Ritter because I married. Sorry for the inconvenience. Yeah, my talk is about synthetic algebraic geometry, and in particular about projective space and line bundles in synthetic algebraic geometry. So in this talk, here's a very rough overview of what you will see in the talk. So first, synthetic algebraic geometry at a glance. I'm trying to give a very quick picture of what synthetic algebraic geometry is supposed to be. Then we will define projective space synthetically. Then we'll talk about line bundles and the Picard group of a scheme synthetically. And then we come to the central theorem, the classification of line bundles on projective space. And then in the end, I will show quickly an application to the automorphisms of projective space. So all results that we will see here are well known in algebraic geometry, that is in the usual external algebraic geometry. We will approach this in a new way. We will present new synthetic proofs using higher types. We will see what that means. So, what is synthetic algebraic geometry? Even though this is a topos theory conference, I'm only going to mention one topos in this talk. It's the topos here, the Zariski topos. The Zariski topos is, here's a definition as a side presentation. It's a topos of sheaves on K algebras. More precisely, we take finitely presented K algebras and the opposite of that. Sheaves with respect to the so-called Zariski topology. And this is the Zariski topos over the base ring K here. So, so often in algebraic geometry, or you always have a base ring in algebraic geometry that you're working over. Often you want it to be a field. That's why this notation K is here. But actually, we don't need any assumptions on this ring. So we can take the Zariski topos of any base ring. It doesn't matter. And by ring, I always mean commutative unital ring. Okay, and the thing about the Zariski topos is that schemes embed into this topos. The category of the category of K schemes of finite presentation embeds into this topos. It's a fully faithful functor, and you don't need to know exactly what is a scheme to see why I'm saying this. You only need to know that schemes are the basic geometric objects that we study in algebraic geometry. So if the category of schemes embeds into this topos, then we can use this topos to study schemes. Also, I wanted to mention that this topos, so sometimes people would drop these finitely presented assumptions here, but we need to put it here to make the functor actually fully faithful. And also, this exact topos here is pretty nice because it's exactly the classifying topos of local K algebras. Okay, so schemes embed into the Zariski topos, and then what we do is we work internally to this topos. More precisely, we interpret Homotopy Type Theory internally to an infinity-1 variant of the Zariski topos. And then internally, we want to develop some theory. We have to start from something. Namely, we will start from a certain ring object R in this topos, which is, from the external perspective, simply the structure sheaf. So this functor here that takes a finitely presented K algebra A and sends it to the underlying set. This is a sheaf for the Zariski topology, so it's an object of the topos. And this is called the structure sheaf of the Zariski topos. And I will just denote it when I'm writing internal stuff that's to be interpreted internally in the topos. I'm just writing R for it. Here are some basic properties, some of which are pretty interesting already, about this ring R from the internal perspective. So first of all, R is a ring, okay, I already said that. And then R is actually a field, in the sense that for every element X of R with X non-zero, we know this element is invertible. So this sounds like R is a field, yes, but we have to be careful. Constructively, there are many different notions of what is a field, right? And classical logic is not supported in it does not hold in the internal world of the Zariski topos. So, for example, we don't have, for an arbitrary element x of the ring R, that x is 0 or non-zero. So we know the non-zero elements are invertible, but we can't decide if an element is 0 or non-zero. The next point here is kind of a generalization. Instead of an element x of the ring, we take vector x of R to the n. And then we know the following. If the vector is non-zero, then the submodule generated by this vector in the module Rn is one-dimensional, is isomorphic to R. So, yeah, this is just a kind of generalization because generating, if we take this module generated and it's isomorphic, this means X is a basis for the module, and that's similar to saying X is an invertible element of the ring R. Okay, next, every function f from R to R is a polynomial. So, to be clear, I'm taking the underlying set of the ring R here and taking arbitrary functions from this set to itself. Every arbitrary function is given by a polynomial. So for an arbitrary function from the set R to the set R, we can find a list of coefficients, a finite list of coefficients, such that the polynomial with these coefficients is the function. So this seems a bit crazy. Yeah, it shows us that the internal world of the Zariski topos is very friendly for algebraic geometry because arbitrary functions behave polynomially. And that's exactly what you would always hope for in algebraic geometry. You're only interested in polynomial functions. You're only interested in functions that are given by polynomials. And here it's just true that every function is given by a polynomial. And again, slight generalization, we can look at functions from R to the m to R to the n. Again, just the sets here, the Cartesian products of the underlying set of R, and they are again given by polynomials this time, n polynomials in m variables. Okay. So, this is the nice internal world of the Zariski topos. And developing more theory inside this internal perspective, we call synthetic algebraic geometry. It's synthetic in that, the language we're using and the way we interpret it in the topos is specifically made for being helpful for algebraic geometry. Okay, so we use this specific language and interpret it in this topos to make definitions, constructions, theorems from algebraic geometry look simpler. Right, I said we want to interpret homotopy type theory internally in this infinity variant of the topos. I'm not going to talk about any details of that. If you want to interpret homotopy type theory, you actually need a model of type theory. So you have to turn this topos, or maybe you could also say we start with this site and want to construct a model of type theory from that. And it's very nice to have homotopy type theory, in particular the univalence axiom. And to be honest, I don't even know all the details of how to do that, but in the paper Foundation for Synthetic Algebraic Geometry, Thierry Coquin took care of the details, how to construct a kind of cubical model of type theory that incorporates this site here, so that in the end, morally, you're interpreting homotopy type theory inside the topos. But since probably not everyone here is closely familiar with homotopy type theory, let me give a short list of key features of homotopy type theory. So, what is it like to work in homotopy type theory? So, it is a formal language for mathematics, okay? It's a language you can use to develop mathematics, and it has the following features. The basic objects that you're talking about are types, and a type X can be a proposition, or a set, or a groupoid, or a two-groupoid, and so on. In general, it doesn't have to be any of that, but, okay, so if I say a type, if you're only used to sets, then you can think, okay, it could be a set. But we also use types to model propositions and so on. And from this point on here, groupoids onwards, these would be called higher types. And actually one point of this talk is to show how higher types can be used to express very nicely some geometric ideas, in this case about projective space and line boundaries. Okay, so if you're scared of general type X, then we can always take the truncation. So the propositional truncation is the universal way to turn a type into a proposition. You could read this proposition as the type X is inhabited. And usually the subscript is dropped. It's just this norm of X, notation for propositional truncation. And then you could instead take the set-truncation or the groupoid truncation and so on. Then we have pi types and sigma types. There's a lot to say about those, but I just want to say very quickly that a pi type like that, so you can form this pi type if X is a type, and for every little x in X we have another type Y of X. Then we can form this pi type, and pi stands for product, so you can think of it as the product of all the types Y of little x. But you can also think of it as generalizing the universal quantifier. So if the Y of X here is a proposition, then I would read this as for all x in X, Y of X holds. But it's more general, Y of X does not have to be a proposition. And dually, sigma type, this is the sum of all the types Y of X. But if you want to have something concrete, what it feels like, it generalizes a subset like that. So if X is a set and Y of X is always a proposition, then we can form this subset of X here, those little x such that Y of X is fulfilled. And instead of this, you write the sigma type here in type theory. Okay, and then the last line here is the usual selling point of homotopy type theory. Isomorphisms between X and Y are the same as identifications. So this means that knowing X is isomorphic to Y is actually the same as knowing X is equal to Y. And this allows you to do formally, precisely, what the general category theoretical theme that we also know from Grothendieck, that isomorphic objects behave the same, right? This is formalized here. So this statement is true in homotopy type theory. Here, X and Y could be sets. Then isomorphism between X and Y just means a bijection between X and Y. But they could also be algebraic objects, groups, rings, whatever. They can also be general types. Then technically I should say equivalence of types instead of isomorphism of types. So then it would read an equivalence between X and Y is the same as an identification between X and Y. Okay, we can also see from this that obviously there will be the situation that I have different identifications between two objects. Right? I can have two different or many different isomorphisms between objects X and Y, so I can have many different identifications between X and Y. That's why they are also sometimes called paths. So an element of the type X equals Y is sometimes called a path from X to Y, which alludes more to the homotopy in homotopy type theory, that you want to regard types as spaces. Okay, so you have to be a bit careful about the equality sign, because X equals Y is not always a proposition. It can have different elements, but other than that, we are in this very nice situation here. Okay, so let's return to algebraic geometry. I want to show some examples of schemes as you can define them internally in the Zariski topos. And we always start from the ring R that stands for the structure sheaf, as I mentioned. So for example, the n-dimensional affine space, the definition is very simple. You take the ring R to the nth power. And if you do this and interpret externally, so in this case, not much is happening yet. I mean, R stands for the structure sheaf, and it just means externally that you take the nth power of the structure sheaf. And in fact, this is the object of the Zariski topos that corresponds to the scheme that's called n-dimensional affine space. It gets more interesting with projective space. So maybe this definition looks a little bit scary at the first glance, but let me convince you that it is, in a way, a very simple definition. So when you explain to someone what is projective space, you always before giving a precise definition, you have to give an intuition, what should projective space be, what should the point of projective space be. And the intuition is that a point of projective space should be a line through the origin in a affine space. A point in projective space is a line through the origin in a affine space. And that's exactly what the sigma type here says. So we're taking the sigma type of those submodules L of the affine space R to the n+1, which satisfy this proposition here. This is the propositional truncation of L is isomorphic to R1. We could also read this here as the module L is one-dimensional, because being isomorphic to R1 means being a one-dimensional module. And then we can pronounce the whole thing as Pn is the set of one-dimensional submodules of Rn+1. In other words, it's the set of lines through the origin in Rn+1. Okay, and in usual algebraic geometry, such a definition here would be the right intuition, but technically insufficient. You need to do a lot more technical setup, a lot more structure to get an appropriate thing you can call projective space. But internally to the Zariski topos, it's exactly right. This naive definition gives the correct object of the Zariski topos that represents the projective space. Okay, there's one point where you can easily generalize here, namely you can replace this number 1 here with something else, and that will be called the Grassmannian. The kth Grassmannian of the module Rn is the set of submodules P of Rn which are k-dimensional. So L here stands for line, and P stands for plane. So the Grassmannian is the set of k-dimensional planes in Rn. And to make it explicit, projective space is the first Grassmannian of the module Rn+1. So it's a little bit annoying that we always have this shift that Pn is defined in terms of Rn+1, right? But this is, it makes sense because Pn really is n-dimensional. For example, if you think of the plane, so that would be R2. So in the case n equals 1, if you have one line through the origin in the plane, then you have one degree of freedom how to vary it. So the set of such lines is a one-dimensional thing. There's a question there?
Is it easy to see internally, or hopefully true, that Pn is also the quotient of an+1 minus the origin by the action of Gn?
Yes, this is true. Pn is also the quotient. So there's another way to define Pn. It's the quotient of Rn+1 minus the origin modulo the action of R times. So you could also say Pn is the set of homogeneous coordinates modulo the correct relation. Yeah.
Also, maybe one comment that, I mean, we can also define Pn like this in classical algebraic geometry. You just have to use the functor of points perspective. But maybe this is what you're saying. But usually it's proven as a theorem after constructing Pn. But this is just the description of the functor of points.
Yeah. Yeah. So yes, indeed, this is very close to the functor of points perspective. And I guess you could say that this synthetic algebraic geometry is an attempt to go a step further in the direction that functor of points already went, right? So we are working internally to the Zariski topos, and the objects of the Zariski topos are the functors that could be functors of points of schemes. Yeah. Okay, so, and maybe I just stress this again. So by using homotopy type theory as the internal language, and this is something that's not usually done in functor of points approach, we can really do very simple constructions internally and then see what it turns out externally. Can prove some things very nicely. All right, let's do some geometry in projective space. So what I want to explain is, if you have 2 points in projective space that are not the same point, if you have 2 distinct points, I want to explain how to interpolate between these 2 points. So given 2 distinct points, how to construct a straight line through these 2 points. Sounds like one of Euclid's postulates, but we want to do it in projective space. And here's what we need to do in the synthetic setting. So remember that P and P prime are actually two one-dimensional submodules. So we can take the module generated by the two. It's, again, a submodule of Rn+1. And we could hope that this is two-dimensional. And I won't explain why, but it is true that if P was not equal to P prime, then this generated submodule will be two-dimensional. So it will be propositionally isomorphic to R2. This means we can take the first Grassmannian of this two-dimensional module, and it will be a subset of Pn, because Pn is the first Grassmannian of Rn+1. And we know something about this subset, namely the propositional truncation of this subset is P1. Because if this module here actually were R2, then, well, the first Grassmannian of it would be actually how we define P1. So we don't have, so the way to read this propositional truncation is we don't actually have an identification between the module and R2, but we know there merely exists an identification. And in the same way, we have constructed from the 2 points this subset of Pn, of which we don't have an identification with the projective line P1, but we know there merely exists such an identification. So we don't have a parametrized line, we just have a line in projective space. Okay, that's it. We say that this subset is the line interpolating between the 2 points. Yeah.
This inclusion is a type?
This inclusion here?
Yes.
Yes. So it's the left thing is a subtype of the right thing, but it can also say a subset because Pn happens to, this type happens to be a set. Okay. Right. Okay. So that's how to draw a straight line through 2 points, and let's apply that to prove something simple or some basic fact about projective space, namely all functions from projective space to R are constant. The classical external phrasing of this fact would be to say that projective space has no, the structure sheaf of projective space has no global sections except the constant ones. Here we can just say functions from projective space to R are constant. We don't have to mention the structure sheaf, we can just use the function type. Okay, I want to actually omit the case n equals 1 because you have to do a little algebraic calculation that's yeah, just as hard as in the external setup. But for the rest, I want to show a synthetic proof. So let a function f be given. It assigns to every point of Pn a number in the ring R. We want to use interpolation, so let's start with 2 points and start by assuming that they are not equal. P is not P prime. Then we can construct this first Grassmannian of the generated module here, which is the interpolating line. And because this interpolating line, just as a set, is propositionally equal to P1, we can apply our knowledge about P1, that is this case we omitted here, to see that the function restricted to the subset must be constant. So we can restrict f to the subset here, then we have a function on something that's propositionally equal to P1. And about P1, we already know that every function on it into R is constant. And being constant is a proposition. That's why it doesn't hurt that we have this propositional truncation here. So for any 2 different points, we can restrict to the interpolating line and see that the function is constant if after restricted like that. So in particular, we know for any 2 different points, the function f assumes the same value at these 2 points. It sounds a bit like we're done, but we have to be careful. So we want to show that the function f is constant. So you could say, well, we're done, because for any 2 points, if they're different, then the values at these points are the same. And if it's the same point, then of course the values are the same. But again, we have to work intuitionistically. We can't use that P is equal to P prime or P is distinct from P prime. This is just not true in this setting. So we have to be a bit smarter, but it's not hard. We fix two distinct points, P0 and P1, and then if we look at an arbitrary point P, you can show that this disjunction here holds. P is not P0 or P is not P1. So the intuition is we have 2 points that are far apart, and then for any point we can decide that either we find that it's apart from this one or apart from this one. And in either case, we can conclude, because if P is not P0, then f of P is f of P0. And if P is not P1, then f of P is f of P1, which is f of P0, because P0 was not P1. So I find this a bit funny. It's a bit like saying we can connect any 2 points in projective space by a zigzag of distinct points. That's what we use to show that the value at any point is the value at P0, so we are done showing that all functions are constant. Okay, so this was a kind of warm-up for the thing about line bundles that I actually want to show, that will use the same interpolation technique. Before I tell you how to define line bundle internally, I have to make sure we know a little bit linear algebra, namely about tensor products. And right, so all we have to know is the following. There's a binary operation on R modules that's called the tensor product. It takes 2 R modules, gives you a new R module. And here's a very basic fact about the tensor product of R modules, namely if we take R1 tensor module, then we have the same module. So R1 is the unit of this tensor product. And actually this is still too general. I just want to use a special case of that, namely that R1 tensor R1 is again R1. So you see, I'm really mostly interested in the module R1 here, which is a very simple module, but it's enough to talk about line bundles. The other thing is that for a module, we can take the dual module, which is defined as the module of homomorphisms from M to R1. And then here's what we need to know about that. The dual of R1 is R1. And we always have a canonical map from M tensor the dual to R1. This is easy to see because the dual was this thing here. And if I have an element of M and an element of the dual, then I can just plug it into the homomorphism and get the result in R1. And then you have to check it's bilinear to actually get this map here. And what we want to know about this map is also only a tiny special case again. So this map is in general not an isomorphism, but if you plug in R1, then it's an isomorphism. Okay. Here is how to define line bundles. We first define internally, and it's Zariski topos again, the type of abstract lines. This here is the type of abstract lines. What does it say? It's the type of those R modules, L, which are one-dimensional. It seems similar to the definition of projective space, but we're not talking about lines embedded in some affine space here. We're just talking about abstract lines. So R modules that are propositionally one-dimensional. What do we know about this type? First of all, it is pointed, meaning just I have an element of this type that I want to regard as the base point, namely the element R1. So R1 is in fact an R module that is isomorphic to R1. Yes, indeed. This type is connected. We made sure that this type here is connected, meaning that any 2 elements of the type are propositionally equal by exactly this condition here. So if I take 2 abstract lines, they will both be propositionally equal to R1, so they're also propositionally equal to each other. I'm saying propositionally equal all the time to stress that for 2 elements of this type, I have no way to construct an identification between the 2. I only have the propositional truncation, so I know there merely exists an identification. Okay, and lastly, if we take this type with this base point, it has this loop space here. The loop space is the automorphisms of R1, which you can see is the group of units in R times the group of units in R. This together suggests a name for the type here, or a notation, namely BR times. So we take the group R times and take the de-looping of that, or we take the groupoid, the pointed connected groupoid corresponding to this group. So the type of abstract lines is at the same time the groupoid corresponding to R times. Okay, and then here's a little bit more structure on this type that follows immediately from the very basic facts about tensor product that I just showed you. Namely, the tensor product operation restricts to a binary operation on abstract lines. Because if I have two modules and I know they're both one-dimensional, then the tensor product will also be one-dimensional. Simply because R1 tensor R1 is R1. And second, we can also take the dual of a line, and it will also be a one-dimensional module again, so we can also take the dual of an abstract line. And here are two laws that hold for these operations that again follow immediately from equations from a previous slide. Namely, R1 is the unit. We have a canonical identification of R1 tensor L with L for any element L, like here. And also we have a canonical identification of L tensor L dual with R1. Okay, if we have these two operations with these laws here, that looks a lot like we have a group structure, right? This looks exactly like a group structure on the type BR times. But I will not say that BR times is a group, simply because it is not a set. When I say a group, I usually mean a set with a group structure. This thing here is a higher type with a group structure. So in fact, it is a groupoid. But we will construct the Picard group of a scheme from it as follows. We are finally ready to define line bundles. And the definition is very simple now. A line bundle on a type X, so X could be a scheme, but can also be any type, any object of the Zariski topos. A line bundle on X is simply a map from X to the type of abstract lines. Again, this is usually the intuition that a line bundle assigns to every point of a space a line, but the technical definition is much longer in the usual setup. Here, internally, the intuition is exactly the technical definition. And, okay, we wanted to define the Picard group. It consists in realizing that the operations from before can be extended to point-wise operations on line bundles. So, first of all, we have a trivial line bundle that assigns to every point the standard line R1. And we have the binary operation of tensor product and the union operation of dualization on the type of line bundles that are, again, defined pointwise. And then we can define the Picard group as the set truncation of the type of line bundles. So we just take this type of line bundles and force it to be a set. And then you can check that we still retain the group structure, the thing that looked like this group structure. And now it's actually a group structure because we forced our type to become a set. And this is the definition of the Picard group in synthetic algebraic geometry. All right, so here you can already see how higher types helped us to express geometric ideas very, very nicely, very intuitively, because this type of abstract lines is not a set, it is a higher type. But using it, we can say a line bundle is really just a map that assigns to every point a line. Yeah, we wanted to talk about line bundles on projective space. And here's the first example of a line bundle. So recall, projective space was the set of one-dimensional submodules of Rn+1. And there's a line bundle called the tautological line bundle on projective space. Namely, it takes an element of Pn, which is a line in Rn+1, a line, so it's one-dimensional, and sends it to the abstract line that is just the underlying line. So you're just forgetting the embedding into Rn+1 here. So indeed, this seems very tautological, and yeah, that's the map from Pn to the type of abstract line. So it's a line bundle on projective space. Furthermore, you can take tensor products of this tautological line bundle, and by this you get a countable family of line bundles. Namely, for every degree d, we define the degree d line bundle in external algebraic geometry. It's usually called a twisting sheaf, a Serre twisting sheaf. And here, yeah, we just take the minus d tensor power of this tautological line bundle. So we use tensor product and dualization in the appropriate way. And here's a fact that I won't prove. The map that takes a degree to the line bundle of that degree is injective. So we actually found countably many distinct line bundles on projective space. And then, of course, the natural question is, are there any other line bundles? And this is the classification question. So what is the, how many line bundles on projective space are there? We already found these countably many distinct ones. And the answer is no, there aren't anymore. So every line bundle on projective space, for every line bundle, there is a number d such that propositionally this line bundle is the standard line bundle O of d. So in other words, the Picard group is isomorphic to the integers by this map. And we will use notation that this d is called the degree of the line bundle L. Right, so this is also a very classical result, very standard, of course, in the usual external algebraic geometry. But the point is how we can, I want to show you part of the proof of this result in the synthetic setting. Again, we omit the case n equals 1. You again need to do some algebra. In this case, it's non-trivial. The main result you need is called Horrocks theory. But for the rest, we want to again use an interpolation as in the toy example before. So here's the plan for the proof except for the n equal 1 case. So first we strengthen the n equal 1 case to a non-truncated statement. So we can say that this statement here, this isomorphism here, is a truncated statement because on the right-hand side you have the Picard group and this was defined as a set truncation of something. We want to get rid of that truncation to get more information, to get a stronger statement about higher types. Then there's a technical step where we have to adjust our given line bundle L so that we can expect L to be the standard line bundle of degree 0 and not of any other degree. And then we can use an interpolation technique to show that it's actually this standard line bundle. I think we will skip parts of the proof, but I think this is interesting. So, as I said, so this again is the truncated, the weak statement about the Picard group. The Picard group is this thing on the right again, is isomorphic to the integers by this map. And we can actually, using this fact here, so any line bundle has the same automorphism group. The automorphism group, you can write it in homotopy type theory as the group of identifications between L and L, namely the automorphism group is always R times. And using this fact, you can extract this stronger statement from the truncated statement. So the stronger statement here is, on the right-hand side, we look at the type of all line bundles. Not its truncation, but the type of all line bundles. And this type is equivalent to the type on the left. So the integers times the type of abstract lines. In other words, giving a line bundle on P1 is the same as giving an integer, namely the degree of the line bundle, and giving an abstract line. Okay, so this is an equivalence of groupoids. These things are not sets. And so this is the map, but I think we don't need the details here. What we actually need from this in the rest of the proof is if our line bundle L on P1 has degree 0, then we have this following strong statement here. For all P and P prime in P1, the line at P and the line at P prime, we have an identification between the two. I said for all for the pi type, which sounds too weak. I should say pi P and P prime. I have an identification of L of P and L of P prime. So meaning that for any 2 points, P and P prime, I can construct an identification. I do not just really know that there exists one. Okay, and so this follows from this stronger non-truncated statement here, because if I know that the degree is 0, then I can see I can see of which form the line bundle has to be here, and then we can just calculate that we have an inhabitant of this pi type. Okay, so the next thing was we adjust our L so that we can expect it to be of degree 0. Yeah, I think I want to skip this. So in the end, you have your line bundle L and you find out what should be its degree, and then you tensor with the standard line bundle of minus that degree to get something that should be of degree 0. And right, so the fact that we want to use is just this line. So, or no, maybe the last line, yeah. So after the modification, the line bundle L will have this property here for all points on a given projective line in projective space. The two lines at the 2 points coincide. So we have an identification here. Okay, then we can do the last step and use our nice interpolation thing. Because if I have 2 different points in Pn, then we made sure in the previous slide that we skipped that the degree of the line bundle restricted to the interpolating line is 0. So we have a line bundle on n-dimensional projective space, and for any 2 different points, we can take the interpolating line, which is propositionally 1-dimensional projective space, and then we restrict our line bundle and get a line bundle on this thing that is somehow 1-dimensional projective space, and we made sure that it has degree 0. So we know that for any 2 different points, we have an identification of the lines L of P and L of P prime. And now it's like before, right? So what we want to show right now is that the line bundle L is the trivial line bundle. And so, yeah, it will also suffice to show that it's constant. This line bundle as a function to the type of abstract lines is constant. And what we have is, for any 2 different points, we have an identification between the values at these 2 different points. But, again, it's not enough, because we can't decide if P is equal to P prime or not. So we have to do something else again. So again, we fix 2 standard points, P0 and P1. And then, so this here is just a rephrasing of this implication here. L is constantly the abstract line L of P0, not on all of Pn, but on Pn without P0. Because if I have a point in Pn without P0, it's a point distinct from P0, and then by this line I know the value at this point is the value at P0. So away from P0, I know my abstract lines are all canonically identified with the abstract line at P0, and the same for P1. Okay? But this is still not enough. What we should do is we should fix, so we should choose identifications of these lines, abstract lines at P0 and P1 with the standard abstract line to get rid of the problem that, yeah, we have these 2 abstract lines and somehow we want to know they're equal, but there could be multiple different identifications between them. That's confusing. So let's choose paths like that. Then we can write something else here, namely the line bundle is constantly the standard line on Pn without P0. So it's trivial on Pn without P0, and it's also trivial on Pn without P1. Okay, and then what we have is that we have these 2 subsets that of course cover the whole Pn, but on the overlap, so on Pn without P0 and without P1, we get 2 identifications of the value L of P with R1. One from the first line here and one from the second line here. And this means that for any point in this overlap here, we get an identification of R1 with R1 that does not need to be the identity, right? The identity map from R1 to R1. It could be another isomorphism. So, in other words, for every point here, we get an isomorphism from P1 to P1, but such an isomorphism is always given by an invertible element of R. And here's another fact. Every function from projective n space without 2 points to the invertible elements of R is constant. So, on this overlap here, we have the situation that we have two identifications, but we can prove that this varying identification of R1 with R1 that varies with the point we're looking at does actually not vary, it's actually constant. And this means we can adjust one of these two paths here to conclude that our line bundle L was constant on total. Right, so yeah, it's a bit more complicated than in the case of just R-valued functions. But again, we have used just this ingredient that you can interpolate between two distinct points. And then in the end, yeah, we had to juggle around a bit with distinct points and identifications and so on. But then we were able to prove that our line bundle is of the standard form. And in total, we have proven that every line bundle of projective space is one of these, in this countable family. Okay. Yeah. What's left is I want to show this application about the automorphisms of. So, recall what I mentioned in the beginning. Every function from Rm to Rn is given by n polynomials in m variables. So, in other words, every function between affine spaces is given by polynomials. And here's a similar statement about projective space. Every function from Pm to Pn is given by homogeneous polynomials, namely by n plus 1 homogeneous polynomials of some degree d in m plus 1 variables. Right. And so this is the way it should be in algebraic geometry. A function between projective space should be given by homogeneous polynomials. Yeah, it's pretty interesting that we indeed have this statement in an intuitionistic setting in this internal world, because it means from this function f we can actually determine this degree of the homogeneous polynomials. And that's also kind of the core step of the proof, namely the degree, this degree d will be the degree of the dual of the tautological line bundle pulled back by this map f here. So that's how you use the classification of line bundles to get this result about maps between projective spaces. Okay, and now the special case for automorphisms of n-dimensional projective space is this corollary here. Every automorphism Pn to Pn is given by an invertible matrix, unique up to scalar multiplication. As a formula, the automorphisms of Pn are the projectivized general linear group over R of dimension plus 1. Okay, and yeah, so here it is particularly interesting that we didn't need any assumptions about the external base ring, because this statement, if I'm not mistaken, is true in external algebraic geometry for an arbitrary base ring, but it's usually proved only with certain assumptions, so over a field, maybe even algebraically closed field, because it's simpler to prove there. But here in the internal version, we didn't use anything about the external base ring, only worked internally with R. And so let me see, is it plausible that the external translation of this statement would be what you would hope? Well, the automorphisms of Pn, I mean, this is the internal type of automorphisms of a certain set from the internal perspective, but externally, yes, we will be able to extract the automorphism group of the sheaf that represents Pn, and on the right-hand side, we have this projectivized general linear group. Yeah, okay, I guess you have to be careful because this projectivization is a quotient, and that will be a bit of work to understand exactly what it means externally. But if you read this statement here, it says, there exists an invertible matrix. So if you translate that to external language, then it will mean locally in the base ring there exists an invertible matrix, and then it should be relatively easy to show that these actually have to coincide up to scalar multiplication. So in this way, you actually get this strong classical result about automorphisms of projective space in a way which is uniform in the base ring, doesn't use any assumptions on the base ring. And at least the whole internal development up to the point where you have to translate to the external world again is quite elegant, I would say. All right. Yeah. I'll just stress again that it was crucial to use higher types in the internal language to nicely express certain geometric ideas in these proofs. And yeah, I personally feel that homotopy type theory is a very convenient language to express such ideas. And yeah, thank you very much for your attention.